In this problem, we are told that we have a sinusoidal current and it's 0 at t is equal to negative 625 microseconds, and it is also increasing at a rate of 8,000 pi. Now, the rate of current change, or rate of increasing, is di over dt. We are asked to find the frequency of it in radians per second, and that's what we're going to do. So to start this off, we are going to start with the following formula, and this can be found in the notes linked below the like button in the description. And for this, we are going to look at the hint, and that's that the rate of current change is di dt. Well, when we look at this formula, we can rewrite this so that the left side has a di dt in it. And we know that our di dt is the increasing rate of change, which is the 8,000 times pi. And this will be set equal to our I max, which we know is 20 amps. It's given to us in the question, multiplied by the cosine Wt plus the theta. Now, we derived this side, however, we still need to derive the right side because what we do to one side, we also have to do to the other side. So on the right side, we are going to have a d over dt, and now we are going to have to derive this. After we do that, this is going to be our equation and our entire derivation. Now from here we want to find our omega. Since we are using the maximum amplitude right here, we are going to want to find the max that our sine can be. Well, to do this we can graph it out. We know that we have a negative sign here. So normally when our sine starts like this, and it will go up and down and up for an entire period, since it's negative, it's going to be the opposite and start going down and then up and down. So we want the highest point here, and we know that the highest point is this pi over 2, which is equivalent to 90 degrees. Now, since we flipped our sign, it's just going to be a sine, and then in here we have 90 degrees, which is equivalent to 1. So that's what all of this is going to be, and we are going to have a 1 right here. That means if we write this out further, we are going to have an 8,000 pi, and then we will divide both sides by the 20. And after we divide these out, we are going to get approximately 1257. Now in part B, we are asked what are the following parameters of the current IT cosine form expression. Now the period of the current source is what we need to find here. And we know our omega, so we can say that our omega is equal to the 2 pi times frequency. And we know that frequency is just 1 over t. So we can replace our frequency with a 1 over t. So now we can find t. We'll multiply both sides by t and divide both sides by omega, and that will give us a t is equal to 2 pi divided by our omega. And if we do this, we are going to get that our t is equal to approximately 0.005 seconds. Now, we want our answer in microseconds, so we're going to multiply this by 1 micro over 10 to the negative 3. So we move our decimal place 3 to the right if we flip this over. And then we're going to get 5 milliseconds for our current source. Now we need to find the phase angle. For our phase angle, we are going to take this equation that we wrote out earlier right here, and then we are going to plug in the unknowns. In the first part, we are told that our current is 0 at our time here. So what we can do is replace this I out here with a 0, and we have our cosine. We're going to leave our I max, our cosine, and our omega. What we are going to replace here is the time now, and it's going to be negative 625 times 10 to the negative 6. That is our new time. So what we can do here is divide both sides by this I of m, so it's just going to be 0 is equal to everything inside of our cosine, and make sure the calculator is in degrees. We are going to take the arc cosine of both sides, and that will give us a 90 degrees on the left side is equal to everything inside of our cosine, obviously without the cosine, because we did the arc cosine for both sides, which gets rid of our cosine. We've found a 90 right here. However, if we look here, we can see that it is inverted. So our actual equation is going to be 90 degrees, so we're going to have a negative 90 degrees here. We also do know our omega right here. I forgot to plug this in, but we know our omega found in part A is approximately 1,257. And this is going to be our new equation here, Now from here we need to move the constants over to our left side. However, there is one thing to note in this, that our negative 90 is in degrees. However, all of this is in radians. So before we finish it, we are going to have to multiply all of the stuff on the right into degrees so that we can add them together. To do this, we are going to multiply the top by 180 degrees and divide the bottom by a pi. This will get rid of the radians, leaving us with degrees. And this will be our phase angle once we solve for it in a calculator. In doing this, we are going to get that our phase angle is equal to approximately negative 45 degrees. And that is how you would go about solving this problem. If you want more network analysis, there's a playlist as well as notes that cover this entire coursework in the description below the like button.